Welcome back. Hope you're doing well. I've left off one slide from 6.4, so I wanted to cover it to give us an example of an adjoint operator here in the space of functional vector spaces so that we can see that there are some examples here where we do get operators in functional vector spaces that do indeed have adjoints. We've seen in our last video an example of an operator inside of a functional vector space that did not have an adjoint, namely the derivative did not have it. However, we're going to look at one now that does have an adjoint to it. And it's going to be this kernel operator that we've mentioned briefly before. The kernel being this function that we integrate by, this k of x comma y, and before we integrate by the function f that we're plugging in for this integral. Remember that, recall that this L of f, what it does is it returns a function back. Linear operators are going to take in continuous functions and return continuous functions. And what this one is going to do is for the x coordinates of this, when I plug in an x value here, that x value goes straight into the first coordinate of this kernel. There is actually a second component of this kernel. This is a function of two variables here. And then we integrate with respect to that second variable there, multiplied times the function, which also has the second variable being plugged in. So this is the example of an operator that we have seen before. What this does is it returns back a continuous function. So this is a linear operator on our space. So this is also sometimes called the integral operator as well. So we have integrals taking place here. We are integrating by k of x, y, but we are integrating against the function that we are plugging in here, this function f that we have. K, again, is going to be called our kernel. Now, if I wanted to go through and attempt to find the adjoint of this, again, my goal, just like last time, is to try and determine what happens if I look at L of f comma g and look to see what happens whenever I write this as L of something times g, and this something being what could be our adjoint operator. If we could get this to be true for all f and g functions inside of our space of continuous functions going from A to B, then this would be an adjoint operator. Last time we noticed that it was not we could get a specific way of writing this for some functions, but it never was a linear operator for all functions f and g. It never did quite work like that. So here we have the question of, can we connect these two things? And let's see if that's possible. Let's take the inner product of LF with G. Now, this is going to involve two integrals. One integral is going to come from LF, this guy right here, and then one is going to come from the fact that the inner product of ends on the continuous functions going from A to B in the complex space is going to also provide an integral. The integral for g is just going to have this bar of g of x outside of it, and that's exactly the same x value that we're going to be integrating for the x we plug in for L of f whenever we consider it to be a function. So that's the same x that's given right here. The rest of it is this kernel operator, this guy right there. Now, how would I go through and integrate this? Well, thanks to the fact that we're on a continuous space, on bounded spaces, everything is bounded continuous, everything is finite, so we could use theorems like Fubini's theorem to switch the order of our differentials like dy dx and make them dx dy. If we do that, we get to this integral right here. Well, guess what? Now we can separate things out that are constants with respect to x, such like f of y. So we could spread out f of y and bring it outside of the first integral here. And you'll notice that we have, in some sense, try to keep our bars consistent through this process. At the beginning, g of x only had a bar right here, but I want to put this kernel operator in the second argument. So eventually, the whole thing is going to need a bar. If I do that, then it turns out that I can be consistent with this as long as I remove the bar from g of x and put a bar above k of xy. If I do that, then I have that this is the integral from a to b of f of y times the complement, or what do we say, conjugate, my bad, the conjugate of the integral from a to b of the conjugate of k times just the normal function g. And that double integral, when I separate out this part right here that now looks like its own kernel operator, or at least the conjugate of a kernel operator. And that's okay, because the conjugate of a kernel operator makes sense whenever we write things in terms of the second argument. So this is something that we could be expecting here. So when I take this and put it into the second argument, I'm going to get to write this in the second argument of this inner product. And what it's going to be is this new operator L tilde. This new operator L tilde is going to look a lot like the normal linear or integral operator, but this time our kernel is no longer going to be k of xy. It's going to have the bar over it. Notice here it's going to have the bar over it because here it's got the bar. And you may have also noticed something else that's a little tricky. Remember, we had to switch our differentials here when we switch the integrals around. So our roles of x and y have changed. What we're plugging into the function is no longer, or the function, each of these operators here, is no longer going to be x. What we're plugging in is actually y. So we're flipping the roles of what x and y play as well. So the L tilde is going to be another integral operator, but this time you switch the two variables and you put a bar over it. When you do this, you see that L star is going to be L tilde, this new definition here. And this is the way that we could prove it. We began with something that was the inner product of L of f with G, and we ended with something that was f comma something composed with G. And that something is that L tilde operator that we've just made. So this is our examples of adjoint operators. Adjoints, of course, are the ones that allow us to pass back and forth an operator from one side of an inner product to another at the cost of adding a star. We learned that in finite dimensional vector spaces that all of these operators that we're looking at have adjoints, but in infinite dimensional vector spaces, that's not always the case. We have some that have adjoints and some that do not. The reason that this is important is that it helps us distinguish something called a normal operator. A normal operator is going to have very neat notions of diagonalizability, meaning we can actually break it apart in terms of its diagonal matrices. You remember that we could do this whenever we had, for example, a basis that we were working with that could be made into, or rather, we could take an operator and write its eigenvectors in terms of an or a basis of our space. And as long as that basis was worked well enough, we could actually write this in terms of a diagonal matrix. Now that we know the term orthogonal, we can actually enhance this a little bit. We can ask the question, when can we write the eigenvectors of a matrix in terms of an orthogonal basis? And that's what we're going to be talking about a little bit today. That's going to be very connected to this notion of normal operators. So let's begin by discussing what a normal operator is. Again, inner product spaces are necessary here because we're about to have to use the adjoint operator, which only works in an inner product space. But we're going to say a linear operator is normal if it commutes with its adjoint. Commutes meaning with the property of multiplication of the matrices of each of these individual operators, so one being L and one being L star. If you multiplied those matrices together in one order, it would be equal to multiplying them in the other order. In terms of looking at these as operators, hence functions, that's in that sense of commuting becomes not multiplication, but composition. So that means that L composed with L star is the same as L star composed with L. These two things are able to go back and forth. If we write just the matrices of these two operators, then we can think of this as matrix multiplication and the ability for those two matrices to commute. There are a lot of special linear operators here in this class of operators. One is whenever you get the adjoint of an operator to be exactly the same thing as the operator itself. For example, we've seen a lot of diagonal matrices, and these definitely fit that bill. 1, 2, 3, with zeros elsewhere, perhaps. This is a self-adjoint operator. If I go through, take its conjugate transpose, then I get the same matrix back. So this would be an example of something that is self-adjoint. Another way to write that is in terms of the inner products. I could write L as being in the first argument of an inner product with vectors x and y, but then I could move the L over to the second argument of the inner product, and usually I have to pay a star in order to do that. I have to add a star to the operator. If it's self-adjoint, well, then L star is the same as L, so I do not have to pay the star whenever I go from one spot to the other. Another type of special operator here is one which is anti-self-adjoint. One that actually becomes negative or gains negative values whenever you take the star of something like this. For example, we might look at something like maybe you have zeros along the diagonal, and maybe you have something like, let's take a look, maybe something like, few ways to do this one. We could just do -1 and 1. So something like this, maybe a rotation operator. If I take the transpose of this matrix, we are going to get to flip these two entries here, and you'll notice that what you get is the negative of the original matrix. So taking the star of this gives us an anti-self-adjoint operator. And then finally, we're going to say that an operator is unitary if whenever you take its adjoint, it's not equal to the operator itself, but rather it's equal to its inverse. Another way to write this that we'll take advantage of later on is that L star L, or is just the identity matrix, or LL star. And whenever we're thinking about these things in terms of infinite dimensional vector spaces, which we could be, then we're not really thinking of these in terms of the matrices of these operators. Instead, what we're thinking of them is as actual functions. So then in that case, L star L would be the identity function, the one that sends all elements of your vector space to itself. In that case, that would be the identity operator. Okay. So normal matrices are going to be the analogs for these for finite dimensional vector spaces. That's whenever when you look at A star A star, you get the same thing as A star A. That means that these two matrices commute with each other. So here's a neat theorem for this that will help us out in the future. Let's let L be a linear operator on a finite dimensional inner product space. So we have our inner product space. We're looking at things like Rn or something like this. And let's suppose that A is the matrix of L relative to an orthonormal basis. Then the operator L is normal if and only if the matrix of that operator is normal. So whenever we can write the matrix A relative to an orthonormal basis, right, we do our change of variables, our coordinate matrix, to write it in that sort of way, then the notion of that matrix being normal is the same as the operator being normal. So these are able to pass back and forth in these finite dimensional inner product spaces. Those special cases of normal operators have slightly different names whenever we consider them either in the world of complex linear functions or in real linear functions, right? Namely, things where you can have complex values inside of your matrices, or if you could just have real entries in there instead. So you'll see here that the names are here slightly different. A matrix A, we'll call it Hermitian if A star is equal to A. That's the one that says that the adjoints are working like this. Now, the reason that this is different is that now that we could have complex numbers inside of here, taking the star, remember, it has us taking the conjugate of each entry there. It'd be skew Hermitian if A star is equal to -A, and we'll keep the same name of unitary if A star is equal to A inverse. Now, if we're in real entries, taking the star is the same as taking the transpose. So we'll write a matrix with a little t up in the top right, and sometimes we will use a capital T instead. For example, B capital T transpose. If we want to talk about the transpose of a matrix, switching its rows and columns, and we'll say that a square matrix is symmetric if B transpose equals B, and skew symmetric if B transpose is -B, and orthogonal, finally, if B transpose is B inverse. Notice that both of these had to be square matrices in order to work. We had to make sure that our number of rows and columns were here on the same side. Now, this is a lot of terminology to kind of keep track of, so let's go ahead and fill out our table a little bit. Each operator, which is normal, has the same name for each of its matrices. For example, if we're looking at a complex matrix, that is a matrix with complex entries, we'll still call that thing normal. And we'll still also call a real matrix, we'll call this one to be normal as well. Okay. Now, for a self-adjoint operator, remember that in terms of the real matrices, we will just say that that is going to be what? Symmetric. That's right. So this is going to be symmetric here. And remember that for complex matrices, we will call this Hermitian. Sometimes, by the way, whenever our operator is working in a complex space, we will also call the operator Hermitian. So self-adjoint or Hermitian might be both back and forth, the same sort of notion there. So we'll use the same word when talking about operators there. And a Hermitian especially will be useful whenever we're looking at a operator that works in a space, in a vector space that is a complex vector space. And then the words for anti-self-adjoint are going to be the skew versions of the words that are for the self-adjoint. Instead of using the word anti-symmetric, which is sometimes used, we will just use the term skew symmetric here, and we'll also say that a complex matrix is skew Hermitian. And then finally, for our last type of matrix here, we'll say that a unitary operator is a unitary complex matrix. Now, we're going to call this slightly different in the real matrix. Remember that we say that something is unitary if A star equals A inverse. We're going to say that it's orthogonal if B transpose equals B inverse. We're going to call that orthogonal. And you might be wondering, is this related to our notion of orthogonality that we have for vectors? And indeed, yes, it is absolutely related. Remember that we say that something is orthogonal if whenever you take B transpose with B, then you're going to get the identity matrix, right? That was our notion of unitary in that case. Now, what does this matrix multiplication look like? Well, isolate what's happening to each of the columns of B. If you look at what happens to each of the columns of B, when you take a look at B transpose, that's going to be that same column, but turned into a row. What this ends up being is when you take a look at this multiplication, what this ends up becoming is that this becomes a lot of dot products of these two vector types. One being the row of each of these B transpose getting multiplied by each of the columns of B. But because the rows of B transpose are exactly the columns of B, if we say that the columns of B are going to be some VI, right, going from 1 to n, for example, then B transpose B is going to be just the inner product of each of those VI and VJ. Well, if this B transpose B is equal to the identity, then what are the values of each of these things? In fact, we can say a lot about them. If I is equal to J, if we're looking at two vectors that are the same, we get that inner product is going to be 1. That's because when I and J are the same, we're looking at elements that are both have the same entry in their row and column, so they're going to be on the diagonal. So that's going to be an entry of 1 for the identity matrix. And then if I is not equal to J, then VI comma VJ is equal to 0. So this will be equal to 0 whenever I is not equal to J. So this gives us a notion of these vectors, the columns of this matrix being orthogonal. And we'll go through and prove that later on, but this is kind of our little teaser for something like that here. Now, not every matrix here gets to play around and be like a normal matrix. For example, if I wrote the matrix I, and 1, if I wrote this matrix down, I could ask the question, is this a normal matrix? Remember that if this is, say, a matrix B, then B star would be negative I, negative I, negative I, and 1. And indeed, if I went through and tried to multiply B transpose, and then went by and multiplied B transpose times B, not transpose, my apologies, B star, B adjoint times B, then I would notice that these two things do not equal each other whenever I try and multiply them back and forth. So there are examples of non-normal matrices. So this is an example of one of those. Okay. So this kind of gets us started here with some examples of each of these types of matrices, as well as soon we'll see, some types of operators that work well in terms of matrix, in terms of normal versus non-normal operators. Now, there's a couple of neat things happen here with normal operators. Here's a theorem that we'll go through and talk about step by step as we go through this little theorem here, these next few slides. Let's suppose we have a normal operator here. There is a relationship between the norm of L of X versus the norm of L star of X. Normally, these functions, these adjoints, can go anywhere that they would like to go. They don't have to be of the same length. But if these two things commute with each other, if L and L star commute with each other, then it turns out that their norms are exactly the same. We'll return to the proof for that in just a second. For the second part, this says that the operators L and L star in fact, actually share the same eigenvectors. They have all of the same eigenvectors as each other. And in fact, you can even relate their eigenvalues. If LV is lambda V, then L star of V is lambda bar times V. One eigenvalue is just the complex conjugate of the other. And then finally, this last part, eigenvectors of L belonging to distinct eigenvalues end up being orthogonal. That means that if V1 is associated to some lambda 1 and V2 is associated to some lambda 2 as these eigenvalues, then the inner product of V1 and V2 is going to be equal to 0 whenever lambda 1 and lambda 2 are different values. And we'll go through and talk about that proof as well. We'll go through and talk about these step by step. But let's start here with the norm of L, x equaling the norm of L star of x. To do this, we're going to go through and just try and do a little inner product argument here to help us out. Now remember that the length of L of x squared, this norm of the function L of x, this is the same thing as the inner product of L of x with itself. We can, of course, bring the L over here to the second argument at the cost of gaining a star, but now we have L star L, which can now be transferred over to become LL star thanks to the fact of this being normal. L star L is the same as LL star. And now I can take conjugates. I can bring back over the L star. Once I'm done with that, I can switch back these two entries, and I have the inner product of L star x with itself, and that gets me the norm of L of x squared. Now, in general, this is true for not just L, but the identity matrix as well. The identity matrix, of course, is just going to give us Ix. The norm of this is the same as the norm of I star of x. And the reason for this is that the norm or the adjoint of the identity operator we saw from our previous video is itself. It is just its own adjoint. The identity is an example of a self-adjoint operator. So what that means is this. Let's say, for example, that we take L minus lambda I. You might see where I'm trying to go with this and start trying to take a look at this operator. Well, L minus lambda I, all of that is normal. In fact, we can write all of this here like this. And if I took the star of this operator, then that's L minus lambda of I star. Well, the star of this matrix is going to be L. Let's see, L is going to be L star. Then minus I is going to stay the same. And then the lambda is going to have a bar over it. Because that is what happens whenever we take star. All of the entries become their complex conjugates. So we should have this equation here. Okay, and we know that this is equal to L minus lambda I times x, thanks to this first part right here. Okay, so these two things are equal. Now, what do we notice about this L minus lambda I of x? What happens if x is an eigenvector? If x is an eigenvector, then we know that L of that vector v is equal to lambda times v. So we know that this should be 0. Well, if these norms are equal, guess what else is equal to 0? L star minus lambda I. So, in fact, in that case, that means we can go back and forth between looking at L star of v. That's going to be equal to lambda bar times the vector v. And that is a proof for that second proof. I didn't see that here in the slide, so I wanted to go through and add that one. So these two things share eigenvectors, L and L star, an operator and its adjoint whenever it should exist. And then finally, for the last part here, V1 and V2 are eigenvectors of L belonging to distinct eigenvalues, lambda 1 and lambda 2. Then their inner product is going to be 0. Let's take a look at what this looks like. Recall that if we have these two eigenvalues or eigenvectors given here, let's say we have lambda 1 and lambda 2 working as such. And let's look at lambda 2 and with respect to the eigenvalue it has for eigenvalue here of bar. Okay. Now, the reason that we can do this is that, remember, these are two eigenvectors of L. And we're going to isolate L star to have the same eigenvector, because it does have the same eigenvector as L. But remember that its eigenvalue that's associated to L, when it's passed over to L star, it's going to gain this little bar right here. So now let's do a little inner product argument. We're going to have lambda 1 times the inner product of V1 with V2 to start off, and we can start transforming this into L of V1, looking at the operator itself. We can pass over that operator with a little star by it, thanks to the adjoint property. But this is equal to the bar of lambda 2 V2, and then the lambda 2 can come out as a conjugate linear association out of the second argument. Now, take a look at what we have on the left and on the right. These two things are, well, almost equal, save for the fact that lambda 1 and lambda 2 are distinct eigenvalues. So this subtraction here should be non-zero. So if these two things multiply together give us 0, and this is not 0, the only thing that can be 0 is the inner product. And that's exactly what we wanted to end up with, that V1 and V2 belonging to distinct eigenvalues are going to be orthogonal to to each other. And that's what we wanted to show. So this gives us a way to separate eigenvectors and eigenvalues. Not only is it the case that eigenvectors are no longer linearly independent from each other, like we saw in a previous video. We also know now that in terms of an inner product space, whenever you look at a normal operator, they're actually orthogonal to each other. They don't contain any component of each of the other ones. Now let's go back and remind ourselves about the adjoint operators one more time. Let me scroll through here to get to one of the neat theorems that we talked about last time, which was this one right here. What we're going to do now is attempt to connect this notion of normality to what we were discussing about orthonormal bases. If you have a linear operator and you look at a orthonormal basis for this V and you start transforming these linear operators, both L and L star, into their matrices for those respective operators, then the matrix of L star is the same as the adjoint of the matrix of L. And that's by matrix adjoint at that point. L here, you have a matrix and you take its adjoint just like you're used to. And here, this is the adjoint operator of L and its matrix that's associated to it. These two things are thought of as equal. So now let's go back to where we are over here. Here's a new theorem for us that's going to use this notion. A linear operator L on a finite dimensional inner product space V is normal if and only if, so we have a characterization here, there exists an orthonormal basis for V consisting of eigenvectors of L. This is even stronger than what we were working with before when we were working with specific matrices, some of which had bases of eigenvectors of L. This says that there exists an orthonormal basis for these as well. Of course, we know by Gram-Schmidt that we could go through and actually take any basis and turn it into something that's orthonormal. But this is going to give us a very neat way of connecting those two pieces using these proofs. So the if and only if means if we can go from the right to the left, and so we can start there. Let's suppose that beta has an orthonormal basis consisting of these eigenvectors. Then the matrix A, remember from our discussion before, is diagonal and consists of the eigenvalues for each of those. Well, something I love about this is that this means what? If we look at the adjoint of L then, and take a look at its matrix with respect to this diagonal operator, well, then we know that that's the same thing as taking a look at L of beta star. Well, what is this matrix? It is this diagonal matrix of lambda 1 through lambda n. So lambda 1 through lambda n is exactly what's meant by this little diag type of notation here. But when I take the adjoint of this matrix, what I get is the complex conjugates of each of its entries. And so that's exactly where this is coming from. And the rest kind of just follows neatly. We have that A star is equal to A star A. Both of these equal. Whenever I multiply these together, I get to look at the diagonal and to take the absolute values of each of the eigenvalues squared. That's what this ends up being when I multiply these two things together. Hence, these two things should compose just like the matrices do, thanks to a previous theorem that we had. Now, the idea of the proof going from the other direction, going from something which is normal and getting a basis consisting of eigenvectors from it, comes from a couple of interesting lemmas. Here's lemma 1. This one is called Schur's theorem and also has different variants and other types of mathematics as well. You'll hear this name Schur quite a bit if you're going into the world of matrices or what matrices end up being in more abstract worlds, which sometimes might be called representations. So Schur's theorem says there exists an orthonormal basis beta for V such that the matrix L of beta, so with respect to this orthonormal basis, its matrix is upper triangular. Now for lemma 2, let's connect that with this. If a normal matrix is upper triangular, then it's actually diagonal. Well, where does this come from? This one's a little bit easier to see. Upper triangular, remember, means that all of its non-zero entries are up here. And then if we were to take its adjoint, remember that that would flip the non-zero entries down at the bottom. Now, after this point, it takes a little bit of time to try and piece everything together, but the only way for us to be able to write something in that form and get something that is normal is if we're looking at a diagonal matrix. These two lemmas together give us what we're looking for. Now, what's the use of a theorem like something like this? What could we do knowing that we could write this as an orthonormal basis consisting of eigenvectors of L? Well, now notice that this proof of the if component is actually pretty cool because we got a little bit more. We also know that its matrix of this operator L is actually diagonal. It's something that just goes along and collects the eigenvalues of something like this. So that's going to actually power us up a little bit when we talk about the diagonalization of these operators, because if we look down at this corollary here, it turns out that whenever we have a normal operator, we can write it in terms of this orthonormal basis consisting of eigenvectors, and we can say a little bit more about these more specific notions of a normal operator. We can say more, for example, about what it means for an operator to be self-adjoint. We say that L is self-adjoint. Remember, if L star equals L. My apologies for pausing so much. I've got something in my throat. So if we have this self-adjoint operator, it turns out that this is the case if and only if all the eigenvalues of L are real. Real means, by the way, that each of the complex conjugates of these entries are themselves. Remember that because this would mean that A plus BI, the bar of this is A minus BI, and these two things are the same if and only if B is equal to a negative B, in which case you have no imaginary component to your number. So how does this follow? How do we get something like this? Well, we just need to see that whenever I take the matrix of L with respect to this orthonormal basis that's guaranteed from my theorem, that this is the diagonal operator of all these lambda 1 through lambda n's. So if I look through and try and take the star of this, if I know that the star of this is equal to the operator itself, the same matrix as what I had before, say if I'm starting with a self-adjoint matrix, then I know that for each of these, because this bar, what it does is it takes the complex conjugate of each of these entries, I know that these two matrices also have to be equal to each other. Well, that means that lambda 1 bar equals lambda 1 all the way up to lambda n bar equals lambda n. So all of the eigenvalues that are collected along this matrix with respect to this orthonormal basis for this operator are all going to be real entried. A similar proof is going to show that L is anti-self-adjoint if and only if all the eigenvalues of L are purely imaginary. Notice that that means that lambda bar equals negative lambda, because if we took a look at A plus BI bar and then tried to form a negative lambda on this, then we would have something like this. If A minus BI is our generic value here, then the adjoint of it would be A minus BI, and it would be equal to negative A minus BI if we took the negative of that generic eigenvalue. Now, here, the B's can be whatever they need to be, but A must equal to negative A, so that means that there should be no real component to each of our entries. So by doing a similar proof to what we had up there, that should give us 2. And then finally, the last thing, if L is unitary, if and only if each of its eigenvalues of L are of absolute value of 1. That means that lambda bar is equal to lambda inverse. This one's an interesting one. Why does this guarantee anything about the eigenvalue? Well, we know that lambda inverse means that it's its multiplicative inverse, so lambda times lambda inverse should equal 1. And we also know that lambda inverse is equal to lambda bar, so we could write this equation like this. Finally, lambda times lambda bar is the absolute value of lambda squared. We know this formula as well. So this gives us that the eigenvalues are of absolute value 1. So that kind of pieces everything together. So another corollary here, we could say that a linear operator on a finite dimensional real inner product space is self-adjoint if and only if there exists an orthonormal basis for V consisting of eigenvectors of L. Turns out that we get an if and only if with this sort of statement, and the reason is that we saw that upper triangular normal vectors. Just 1 second. My apologies on that. The reason behind this corollary is this number 1 corollary here, the first part of corollary 1. Because whenever we take a look at a self-adjoint operator on a real inner product space, we're automatically going to have all of our adjoints. We're going to have eigenvalues and enough of them to work through this, thanks to the fact that it is a normal operator. So we have an orthonormal basis for V consisting of eigenvectors of L, and our eigenvalues are all already real. So we could go backwards as well, because any eigenvalues that you have are already real. So that is going to give us that we automatically have a self-adjoint operator whenever we can be looking at all of these eigenvalues. So this kind of characterizes our notion of when we can have a basis consisting of eigenvectors of our matrix. And it happens whenever we're looking at, whenever we take our linear operator and turn it into its matrix in a finite dimensional real inner product space. If we look at it and say, oh, the transpose of this matrix is itself, then we know there exists this basis for V, or more clearly, an orthonormal basis for V consisting of these eigenvectors for L. So let's go through and see a couple more things here. Let's try and piece together a couple more pieces of the puzzle as we continue to build toward one of our big theorems for this week, which is going to be how we can diagonalize these matrices. We're still not quite there yet. So far, we've only decided that all of these normal matrices can be written or have a orthonormal basis consisting of eigenvectors. Now, that's very strong, as we've seen in previous weeks, but we want to continue kind of diving into that. So there's our theorem, part A from before. And there's part B for the corollary 2, when working in these in terms of complex or real parts separately. And here's an example of one of those things. Here's a matrix A equals, and then we have this symmetric matrix down here. We could go through, calculate what it is, how its eigenvalues are, and then get 0, 2, and 3. And we could get associated eigenvectors for each of these things, put all of those together. And then when we do that, we can break these apart and get vectors 1 over square root of 2v1, 1 over square root of 2v2, and v3. These vectors end up forming an orthonormal basis. The reason for these constants is that the length of v1 is square root of 2, as is the length of v2. Now, to bring this example back to what we were seeing before, I've gone ahead and written down what each of these are in terms of the diagonal matrix that we can get. We could take our matrix, this is our symmetric matrix, and since we have an orthonormal basis in terms of our eigenvectors, we can write out this matrix in the following way. Here's what we can do. We can take each of these elements, our vectors of our orthonormal basis, and have each of them form a column of kind of a transition matrix, right? We can transition this matrix to be now in terms of this orthonormal basis. And what we should get out of that, or what we would expect out of that, is our diagonal matrix of eigenvalues. And indeed, that's exactly what we get. So notice here that I put my transpose, or my inverse matrix, if you will, on the right-hand side, on the left-hand side, since we are using that to transform this matrix using our little map of U and U inverse that we have drawn before. And when I go through and multiply all of this out, I get all of my diagonals in the spot, or diagonal entries to be the eigenvalues associated in the spot corresponding to which eigenvector is associated to that eigenvalue in each of those corresponding positions. So those are the sorts of pictures that we've been having before, and we're seeing that take place here. The reason that we know that we have it for sure is that this is a symmetric matrix now. Here's another one. Here's one that if we go through and take a look at it, we might notice that this one is not necessarily maybe a symmetric matrix. If I take its transpose, notice that actually I don't get the same matrix back, and I actually don't get the negative of the matrix back either. Instead, what I end up getting is an orthogonal matrix. All right, and here's how we could go through and show that. Remember that we say that we have an orthogonal matrix, and A times A transpose is equal to the identity, in which case A transpose A would also equal the identity. However we'd like to write that. So let me show you this real quick. We can write compositions of these two matrices in the following way. You may remember, by the way, that geometrically, this can be done a little bit faster than it can be done algebraically. Recall that a phi we derive to be the rotation of a vector by an angle of phi. So if we take its transpose, we could ask the question, okay, what happens when I take its transpose? Well, it turns out that if I multiply two matrices together, I will get just adding those two angles together for phi and psi, and there is that algebraic way of writing it here that we have done in the past. We also get that A sub 0 is the identity, okay? And then here is a phi. Again, we can write the transpose of each of this stuff and realize that this gives us the same equation here. So A transpose is A inverse, because these two things are the same. And so because of this, we know that A is an orthogonal matrix, thanks to some of these calculations that we've been going through here. So we have that you can compose two matrices of different angles and put them together, and they become a matrix of the sum of those two angles there. We also have that the inverse is A of A sub minus phi, which is the same as the transpose, hence A sub phi is orthogonal. And we know that for orthogonal matrices, well, one, we're working with something that is normal. It's star, quote unquote, the transpose in a real vector space is definitely going to be normal with it because these both equal the identity. Both of these are the identity. So we can go through and write this using the fact that this is an orthonormal space. Now let's take a look at that a little bit more. Let's go through and calculate what each of these matrices should get, especially when we look at our characteristic polynomial, the determinant of A sub phi minus lambda I. When I go through and do this, notice that my eigenvalues here, lambda 1 and lambda 2, are not actually real eigenvalues. These are real, they have real components and they have complex components. And why is this? Remember that we would say that a normal matrix has a set of orthonormal vectors or an orthonormal basis, excuse me, that form a basis for our space whenever we were in a complex vector space. Now, if we were in a real vector space, we would need not normal, but we would need self-adjoint. We would need for this to be self-adjoint. Remember, we said this matrix right here cannot be written as a self-adjoint matrix. And so because of this, we need to be considering this in terms of the complex vector space. We're looking at this as M2 of C rather than M2 of R. So these eigenvalues end up having complex components for each of them. We can go through, find what their eigenvectors are. We get to one negative I and one I. And indeed, when I divide these by their lengths, can find that these two form an orthonormal basis for C2. So I can get the same sorts of formulas that I have for my previous ones, but notice that even though all of my entries in this matrix are real, they do not work unless they do not give us an orthonormal set, orthonormal basis of eigenvectors unless we look at the complex numbers. Remember that we looked back at this matrix before, in fact, in a previous lesson, and we noticed that in terms of the real numbers, there were no eigenvectors at all. So we couldn't even start trying to form a basis. But when we extended to the complex, we were able to do so. You may remember these computations again from when we just flashed them on the screen a bit ago, or from when we did them in a previous video. I think this was about in week 4. And when we computed a few things, like we could see here, for example, that when you plug in the vector or the angle 0 for this matrix, you just get the identity operator back. The fact that it has inverses and is orthogonal come from this sequence of calculations here. We can calculate its characteristic polynomial as we have done in the past. We can find its eigenvectors. Here's a little bit of that math here, and I like that the math is here because we can see this calculation go one more time and get a little bit more familiarity with these eigenvectors and how we are going through and calculating these. And we can note a few things here too as well. So here's I sub phi, v sub 1, has these values right here. And we see that this calculation down here that, for example, that this last thing is equal to lambda 1 times v1 comes from lambda 1 being this eigenvalue right here. For example, cosine phi plus I sine of phi, this is lambda 1 times 1 up here on the top. And then sine phi minus I times cosine of phi. Well, this is our first term had a 1 in front of it beforehand, and now it's been multiplied times minus I, so we might expect this to be minus I times lambda 1, and indeed, that's exactly what it is. So we have the vector 1 minus I being a good vector here in terms of this formula. Now, we can check and see that because our matrix A phi has real entries, you could say something too about what your second set of eigenvector versus eigenvalue is. Because everything is a real vector, right? Or everything in A sub phi is a real entry. What happens if I take a bar over everything in this equation? Well, if I take a bar over everything in this equation, I'm going to get A sub phi bar, B sub 1 bar. And I'll go ahead and keep the bar right here, equals lambda 1 bar, B sub 1 bar. This equation should lead us directly to this equation. We just took a bar of both sides. The reason that I bring it up, though, is that because all entries inside of A sub phi are real, I don't need the bar above A sub phi. So what does this mean? I can now find another eigenvector and eigenvalue combo based on the fact that A sub phi had real entries. I've already found one. I found one eigenvalue to be where cosine phi plus I sine of phi existed, but I already know lambda sub 2 then. It's just going to be the complex conjugate of this. It's going to be cosine of phi minus I sine of phi. And then what is its eigenvector? Its eigenvector is going to be the complex conjugate of this is going to be 1 comma I. So that's how we can use the fact that matrices are real entries to kind of get us to that faster point. And so we could go through and calculate that if we would like. Each of these has a length of 2. So if we divide by 1 over square root of 2, then we get an orthonormal basis for C2 in that regard. So now let's talk about some unitary matrices. We've just seen one that was orthogonal. That means in the real case, we were considering it to be unitary. But even when we moved it over to M2 of C, it actually remained unitary in case of everything being real entry. Then we know that A transpose A and A star A share a lot of the same qualities. Namely, if everything is real, then all you're doing is taking a transpose of your matrix. Taking a complex conjugate doesn't do anything if your entries are already real. So let's talk about how we can characterize unitary matrices. We've gone ahead and seen some parts of this theorem before, but now it's formalized. Given an n by n matrix with complex entries, we say that the matrix is unitary if and only if the columns of A form an orthonormal basis for Cn. Remember, we did this for the real case whenever we were working through the rows and the columns of that. And then the rows of A do the same thing. The rows of A do the same thing. This is because when we did our proof before, we were doing A transpose A, but we could have also done A transpose and then considered each row inside of A star, which also became the columns. Rather, okay, so the rows inside of A, which become the columns of A star. And that's exactly the sketch of our proof here. The entries of the matrix A star A are inner products of the columns of A, whereas the entries of A star are inner products of the rows of A. So whenever this A star A is equal to the identity, that's true if and only if the columns of A form an orthonormal set. Remember, this was our picture of Vi, comma Vj, and this is going to be 1 if and only if I is equal to j, and it's going to be 0 at any other time. And that happens exactly when you have the identity, when you multiply these two matrices together. So this will imply for us that a unitary matrix is a transition matrix, changing coordinates from one orthonormal basis to the other. Remember, that's because whenever you take an orthonormal basis and put its columns up and down through the rest of a matrix, then that's exactly a transition matrix. So all of our transition matrices are unitary. You may have even been a little confused when I wrote up here a couple of slides ago, when we were doing our change of matrix, our coordinate matrix, to turn this matrix into its diagonal matrix full of eigenvalues, may have been confused that I wrote transpose here instead of inverse, like we've written before. And the reason is that it didn't matter, because this is a unitary matrix. This is one where A inverse was A transpose, because we were in a real vector space at the time. In terms of complex vector spaces, of course, we would be looking at things like A inverse equaling A transpose instead. So that gives us a way of looking at coordinate matrices in a slightly different way. Coordinate matrices are just unitary matrices. Their asterisk, their adjoint, is going to be the inverse of those matrices. So now I can return finally to get to our big theorem here to talk about normal matrices. And this is going to be all connected back and proven thanks to the fact that normal matrices, we know, first things first, have a orthonormal basis of eigenvectors. So what could we do if we have an orthonormal basis of eigenvectors? We could use them to form a transition matrix. A transition matrix is unitary, and the matrix that you get after multiplying by U star, that matrix, and U, what that gets you is a diagonal matrix full of the eigenvalues. So you will see here that that connects most of the theorems here, the parts here in this theorem. If A is normal, then there exists an orthonormal basis filled with eigenvectors of A. And then you can use that as your unitary matrix, a transition matrix, to get your diagonal matrix full of eigenvalues. So A is equal to U du inverse. And another way I could write that, of course, is U du star, since U is unitary. Now that works the same way in terms of a real entries here. But remember that we don't get this orthonormal basis for our n unless we're looking at symmetric matrices, one where A transpose is equal to A. So we don't get something as strong as, say, something that is normal in terms of the real entries. Because remember, those eigenvalues, just like we saw in the previous example, those eigenvalues could still have complex components. So they may not have this diagonalizability unless we consider them as entries or as having complex entries or in a complex vector space. So here we say that this is an if and only if A is symmetric, then there exists an orthonormal basis for Rn consisting of its eigenvectors. And hence we can write this as this diagonal matrix and an orthogonal matrix such that A is equal to U to U inverse. So this is kind of like our complex form of this theorem versus our real form for this theorem. Now we can continue talking about unitary operators a bit more because now we know that they're pretty interesting. They are change of basis matrices. These are coordinate matrices that take us from an abstract finite dimensional inner product space and have us write them in terms of Rn. So let's talk about them just a little bit more. Let's see if we can characterize what unitary operators are with how they work, especially in terms of inner products. Now, if L is unitary, then we actually get this equation. Where's this coming from? We have something like Lx, comma, Ly. And what we can do is we can move the L over at the cost of a star. So we can get L star L of Y. But remember that L star is L inverse. So this actually is just the identity operator, and we're just looking at X comma Y. So applying a unitary matrix or applying a change of basis operator to both parts of X and Y does not change the inner product. That's a neat thing as well. So that's a little neat corollary that is, I don't think, quite put into this theorem, but I can just say it here, that a change of basis or a coordinate matrix, applying a coordinate matrix to the entries of a inner product space does not affect the inner product of elements in that space. If both X and Y are sent through a change of basis matrix or a change of basis unitary operator, then the inner product between those sent elements, the ones sent through L, is the same as the ones before they were sent over. Their inner products remain the same. This in particular applying to L of X by itself, if I just replaced Y with X here instead, then I would get part 3 for free, because I could just say L of X comma L of X, that inner product is the norm of L of X squared, as is the norm of X and X, which is the norm of X squared. So that gives us what we're looking for there. The matrix of A relative to an orthonormal basis is unitary. We've discussed how we can write these operators in terms of their matrices and carry over their properties. L maps orthonormal bases to other orthonormal bases, right? In fact, this does it for some or any. These things are equivalent because, take a look at this, if X and Y have an inner product of 0, then that means that L of X comma L of Y is also going to be equal to 0 because these two things are equal. So this is sending sets that are vectors that are orthogonal to each other, two vectors that are orthogonal to each other. And then what's more, if, for example, I look at X comma X, I look at the same thing, I know in an orthonormal set that's going to get me 1, but that's also equal for L of X comma L of X. So this gives us a notion of orthonormality between the range elements inside of when you take an orthonormal set and send them through a unitary operator. Now, this can work for some, this can work for any. If I just show that this operator works for some orthonormal basis, then indeed that can show that this operator is unitary and hence it works for any orthonormal basis here. So we can see here that little bit of the proof of how L star and L work together. All right, so we're kind of just starting to get to our point of wrapping up here, talking about these unitary matrices now instead of unitary operators. But unitary matrices, thanks to the fact that operators grant their matrices many of their properties, namely those that we've been talking about today, like self-adjoint. Self-adjoint becomes symmetric, or then anti-self-adjoint becomes skew-symmetric, and so on and so forth. The same thing happens here with unitary. If we take a look at a n by n matrix A with complex entries, then the following are equivalent. If it's unitary, then A star is equal to A inverse, and the columns form an orthonormal basis, as do its rows. So unitary matrices are our transition matrices, and vice versa. Transition matrices are our unitary matrices. Now we have a way and a point of connection between two different square matrices. We could say that two matrices are unitarily equivalent if essentially they're just a change of basis away. If A is equal to UBU inverse, then we'll say that these two are just a change of basis away. We could have moved things around, changed our coordinate system a little bit, and really these two things are doing very much the same thing, just with respect to a different orthonormal basis on our vector space. So it's a special case of the two matrices being similar. Remember, we said before, we were looking at things like invertible matrices, being able to send that here. But this is special because we're not only just asking for these matrices to be invertible, we're asking them to be unitary, which means that its inverse is something special. It's the adjoint of the matrix, that those two things are the same. So our theorem here is that the matrix A is normal if and only if it is unitary equivalent to a diagonal matrix. That's using that part 3 of that theorem that allows us to write the matrix A as U inverse. In terms of the real vector spaces, we would say that matrix A is orthogonally equivalent whenever you can write it in terms of the real vector spaces version of unitary, which is orthogonal, if you can write U as an orthogonal matrix. And this gives us another characterization of a matrix being symmetric or self-adjoint. And that happens if and only if it's orthogonally equivalent to a diagonal matrix. So this is a very special type of similarity once again. And these two things are orthogonally equivalent if and only if the matrices are the same linear operator. When I say they're kind of doing the same thing, it just means that the orthonormal bases are looking slightly different on these spaces. But that kind of does it for us today. The idea here is that for unitary matrices in particular, these are interesting because we've been able to pair these with transition matrices. But the only way we were able to get to this information at all is that we could talk about normal matrices being diagonalized. And the way that we were able to do that was we went through and discussed how normal matrices have a orthonormal basis of eigenvectors for it. And went through and discussed how that would work. L and L star get to share the same eigenvectors. There's a way for us to use these and break these apart. The adjoint is a very special type of operator thanks to the fact that an inner product works in our space. And connecting all of these together got us to this really big theorem that we were discussing here today about how we could be diagonalizing these operators or their matrices. And that will do it for me today. Thank you so much. Have a wonderful day.